Hello, I'm Sue Nelson, and in today's Planet Earth podcast, I've got a wonderful bird's eye view of Oxford and the university's famous dreaming spires. Well, at least some of them. We've got the spire of St Mary's Church, the dome of Radcliffe Camera, New College Chapel, and the tiny green dome of Queen's College in the distance there, as well as the more modern buildings and 4 almost Titanic-like silver funnels of a chemistry building just across from where I am now, and that is the roof of the Department of Earth Sciences. And it's not just because of the scenery, as you'll discover in just a moment. Also coming up, although down on the ground, Richard Hollingham will be getting his hands cold and dirty when he meets a man who collects tubes of sediment from riverbeds.
So here we are then, we're now looking in the freezer, and you can see there's over 57 sediment cores in here, each of about 1 metre in length, and then they're sealed at both ends, and the tubing is a polycarbonate tubing with a way up arrow so that we know which is the top of the core and which is the bottom of the core.
Before all that, a brief memory test. I want to know if you can recall exactly what you were doing on April the 14th last year. Any idea? Well, if I mention that this was the day a certain volcano in Iceland coughed up an enormous ash cloud that closed most of Europe's airspace, then I'm sure your memory will spring into action. It certainly works for me, as I was stuck in Lisbon, and what was supposed to be a 24-hour trip turned into a 6-day journey back home, most of it by bus. And the cause of mine and millions of other people's disrupted journeys is why I'm up on the roof with Professor David Pyle and Dr. Tamsin Mather from Oxford University. Well, to be more precise, it's actually what comes out of an erupting volcano into the atmosphere that's brought me up here. Start with you, David. When a volcano erupts in a sort of spectacular fashion like it did in Iceland, what is it spewing out?
In the case of the Icelandic eruption, the summit crater was actually full of ice. So what we think probably happened was that the hot molten rock emerged into the crater, began to cool very, very quickly against the ice, melted the ice, and produced a mixture of steam from turning the ice rapidly to steam, which would be the white clouds coming out of the volcano. And then the rock itself, when you cool it quickly, it actually breaks up, it fragments. And so that then produces pulverized rock, which we call ash. When it's coarser, we use the Icelandic word tephra. And then most of the material that was actually ejected out of the volcano would be a mixture of steam, volcanic gas, if there was any gas associated with the rising molten rock, and then fragmented rock.
Now, both of you are interested in something in particular that comes out of the volcano called aerosols, which immediately makes me think of an underarm deodorant, but that's not the case, is it, Tamsin?
Aerosol is a suspension of particles in a gas. That is essentially what you have when you use your underarm deodorant, is that the spray can creates lots of tiny, tiny droplets of liquid in the air, which then do their job in terms of keeping us all sweet smelling. But volcanic aerosol is a bit different. So as well as the ash that you get various other parts of the plume that come out as gas and then condense to form very fine aqueous droplets, so water droplets if you like. These droplets can be very strongly acidic. So they have related but slightly different effects to the volcanic ash.
And what types of gases are you talking about?
So in volcanic plumes, the major gas is steam, so water, vapour, and then carbon dioxide, but these are actually relatively inert in the atmosphere. They don't really react very much. One of the key culprits when it comes to forming aerosol is sulfur dioxide. So sulfur dioxide is a gas, but it undergoes chemical reactions in the atmosphere. It oxidizes, and when it oxidizes, it forms sulfuric acid, and sulfuric acid basically likes to form these little droplets, acidic droplets that we call aerosol.
David, normally you do most of your work in South America. So when a volcano like this erupts virtually on your doorstep, do you sort of think, well, that's interesting, but it's not the ones I study, or do you spring into action?
I haven't previously worked on Iceland, but in this case, it was the opportunity of having the ash cloud move from Iceland across northern Europe, across the UK, and then out across northern Europe, that gave us probably a once in a lifetime opportunity
Let's hope it's once in a lifetime.
once in 50 years maybe, an opportunity to collect fine particles of ash that have travelled between 1,000 and 2,000 kilometres from the point of emission and before it actually reaches the ground. So we have very little idea of how the actual processes that take particles very long distances then eventually bring those particles to the ground. We don't know, at 1,000 kilometres from the volcano, we simply don't know whether the particles fall as single grains or have they stuck together as clumps of large ash particles, and what's the relationship between the grains of ash that actually reach the ground and the ash that we can see from the satellites that might be still a few kilometres above the ground. So we can use our observations to test our understanding of how we think these processes happen.
How did you sample the ash then? Did you simply come up to the rooftop like where we are now and literally sort of wet your finger and put your finger out? Because I know that while I was stuck in Portugal, I was getting texts and emails from people saying, my car's covered in ash.
No, in fact, in my case, I was actually in an enclosed room in the Diamond Light Source synchrotron lab doing a different experiment. But I managed to get on email and contacted our postdoctoral researcher, Melanie Witt, who's an expert in air sampling at volcanoes. And so we have a lab full of filters and pumps which we normally take into the field, and in this case the field area was Oxford, and the best place to do it was the top of the Department of Earth Sciences.
And you used a sort of larger version of the pump that you've brought up to the roof with us now, which I've got to say is spectacularly unimpressive in that it resembles, well, it's a large battery pack, about half the size of a bag of sugar, with a couple of big crocodile clips on it, an orange cable, and then it's hard to describe what that is. You say it's a pump, and you can see two tubes at the top, like filter tubes. Otherwise, it could be one of those paddles that people use to give heart emergency cardiac arrest treatment. It's like one half of a paddle like that. So how does it work?
This is an air sampling pump, and you can hear it. I'll just turn it off so you can hear it. But we use this air sampling pump to suck air at about 20 litres a minute through a series of filters, and it's a way of collecting direct samples from the atmosphere.
So sort of a reverse vacuum cleaner action.
Yes, and in fact we have used a handheld vacuum cleaner in the field for air sampling before.
And do you have any of these particles still here in the laboratory?
Yes, we do. Yes.
Well, in that case, I think we definitely ought to go and see them. Dr. Tamsin Mather, thank you very much indeed. And while I head downstairs with David towards the lab to see that volcanic ash, let's hear about a different form of material, one that settles to the bottom of rivers. I'm talking about sediment and how, in the right hands, it can act as a veritable time machine. Richard Hollingham discovered this intriguing property when he went to Nottingham to meet Dr. Chris Vane, a senior organic geochemist at the BGS, the British Geological Survey.
We're in the environmental handling facility at BGS, and what this is simply a freezer which contains sediment cores. We keep the cores frozen so that they preserve really well, rather like with food, the organic chemicals in the sediment core.
So let's open this up. It says Thames pollution on the lid,
right.
Big chest freezer.
So here we are then, we're now looking in the freezer, and you can see there's over 57 sediment cores in here, each of about 1 metre in length, and then they're sealed at both ends, and the tubing is a polycarbonate tubing with a way up arrow so that we know which is the top of the core and which is the bottom of the core.
So these are like clear drain pipes, really, about a metre long. Can I pick one up?
Absolutely, yeah.
So this is from the Thames.
That's right, that's from the Thames. This is as it would be standing upright, so this would be the very surface of the sediment, and here we're going down in time, down to 1 metre in depth.
So you stood on the banks of the Thames and drilled this sediment out?
Yes, we simply use a hand coring device and push through the sediment. In most of the Thames estuary, the sediment is very soft, and we're quite easily able to extract a plug of sediment like this, which captures all the historical and geological detail within it.
So it's 1 metre long. How far back does it go?
Well, we dated some of these cores using radionuclides such as cesium-137, lead-210 and also lead isotopes. And we're probably going back here to before the start of the Industrial Revolution. So around about 1750, let's say, would be at the base of this core. The depth at which that onset of the industrial occurs will vary in each of these cores because there's different sedimentation rates within different parts of the estuary itself.
So you've got here a record, an historical record of what went into that sediment.
We go from the modern electrical age and pollutants associated with that through to, in the mid-1950s, to around 1850, use of coal and things like this, and looking at the chemical fossils of that. And then even before the Industrial Revolution, there'll be a large number of chemical fossils associated with agriculture and things like that.
A record of humanity on the Thames.
A record of humanity on the Thames and how society and urbanisation of London has changed through time.
I'll let you put that down because it's very cold.
Yes. Yeah.
And let's go back to the lab and see what you do with this data. And this is the Organic Geochemistry Laboratory, which is a white lab full of white boxes, and these are the analytical equipment with tubes and dials and buttons on them. There are sample bottles. There's even what looks like an oven over there. Why an oven?
It's very important for us to know the weight of the sample of the dry sediment, so it's useful to simply have a drying oven just to drive off the water so that we have a standard weight of sample before we put it into this sophisticated instrumentation.
And from this, you can tell what chemicals are in those tubes of sediment.
Right. Go down those sediment tubes and take slices of that sediment, and then what we do is we analyse that on this instrumentation, and from that we can look at different chemical relics of the past. For example, we can look at chemicals from major use of coals called PAHs. We can look at chemicals from hydraulic systems and industrialization called PCBs, polychlorinated biphenyls. All of these compounds are actually to a certain extent harmful to humans and ecology. So we can use that not only to help protect the environment and people, but also to put a historical date on sediments down those tubes.
Traditionally, I suppose geology is all about dating things to millions of years. You've got these ages of millions of years, if not billions of years. And yet you're talking about dating small eras, really,
That's right.
Eras of humanity and that humans' influence on the environment.
That's right. What we're talking about here is basically dating something called the Anthropocene. It's this notion of basically the current period we're living in which man has altered it, and then that alteration is preserved in the sediment. So yes, here we're dealing with something which is very tangible to people. It's within our own history and possibly our grandparents' history and maybe their grandparents, but not necessarily any further back than the Industrial Revolution.
And I suppose within that you've got the Industrial Revolution, you've got coal, you've got more recently nuclear. You can see those.
That's right. We can see different markers. So we've got the coal age with elevated PAHs. We've got, if you like, the fuel age, major use of vehicles. And we can tell that from total petroleum hydrocarbons and lead isotopes. Then we've got markers of the nuclear age through radionuclides, and then these markers of the electrical age through PCBs and other compounds such as flame retardants. Many of these compounds are resistant to biodegradation, and so they're preserved in the sediment record, and those tubes, those plugs of sediments from the Thames estuary. We're looking at a range of different estuarine systems. We've already looked at the Mersey. We're still working on the Clyde, so a range of different locations in the United Kingdom.
Now, this idea of the Anthropocene is interesting in itself, but can you use this information about pollution within these sediments? Is it relevant to the future?
Yes, it's very relevant to helping us manage our estuaries and rivers better, because although, as you see from the data, many of the pollutants are preserved maybe a metre or so down in depth, these river and estuarine systems are liable to change as sedimentation changes, and they can actually be remobilised and moved to the surface, where they can impact both upon the ecology of the estuary and river, but also upon humans. So although it seems like it's something which may have been deposited maybe in the 1930s, it's still relevant to us now because it can still impact us.
So you look at highly toxic chemicals like PCBs, which were around in, the 1950s, 1960s?
Yes, 50s,
They're
60s,
locked in the
70s.
sediment at the moment, but disturb that and they're released again into the environment.
Absolutely. So it's very important then to understand the process via which those are transported through the estuarine system and how they are then remobilised. And with things like increasing temperatures, the temperature of the water and the temperature of the sediment can actually alter how the PCBs partition between the water and then being locked into the sediment or not. So we need to understand basically where they are in time, and also the process via which they could be remobilised and affect humans.
Chris Vane from the British Geological Survey, ending that report from Richard Hollingham. You're listening to the Planet Earth podcast from the University of Oxford, and I've come down from the roof now with Professor David Pyle into the laboratory to see some of the ash that was collected on the roof from the Icelandic volcano eruption last year. Where is the cause of my travel disruption? You've got a little plastic bag, what looks like sellotape.
Yes,
Is that the
that's
filter?
Right. Just 2 pieces. These are actually just 2 pieces of sellotape, which a colleague used to collect the volcanic ash from their car windscreen in early May. This is a second phase of the eruption.
Is that the large, well, compared to what else is on that bit of sellotape, the large dark grain that almost looks like a sort of black sugar or salt grain?
No, in fact, those large grains will probably be bits of wood or something that's just carried around in the atmosphere. But what we have here is a couple of strips of sellotape, and it's kind of the pale brown background material.
Oh, wow. So the stuff that I just thought was general background fluff, as you would, is actually all the ash.
That's right, yes, yes. I don't think we've ever had an opportunity quite like this, where we've had observations and samples collected from the volcano itself during the eruption, where we've had satellite measurements of how the ash cloud is then moves through the atmosphere from the volcano and then thousands of kilometres downwind.
It's sort of an evolving experiment, effectively, isn't it?
That's right, yes, yes. So we've got a great opportunity to use the measurements in the laboratory to work out whether the ash particles landed as single grains or as clots of grains all caught together.
Why do you need to know that?
It's actually very important both for understanding the hazard to aircraft and also for understanding whether there might be any tiny effect in terms of human health. So very fine particles that are particles that are less than between 2.5 and 5 microns or so are actually small enough to be inhaled into the lungs. Now, normally we don't actually see particles that small preserved in the geological record after volcanic eruptions. They travel too far downwind and they fall into the oceans. They're probably consumed by organisms or they dissolve once they're on the ground. But in fact, in this case, if those very fine particles have actually clumped together in the ash cloud, then that clump of particles will behave as if it were a larger particle, and it will then land on the ground after 1,000 kilometres rather than after 5,000 kilometres. And once it's landed on the ground, there's a chance that the fine particles will then separate, and you'll have a higher than expected concentration of very fine particles at ground level. And so this is one of the things we want to investigate.
David Pyle from the University of Oxford, thank you very much. And that's the end of today's Planet Earth podcast. Do get in touch with us via our Facebook page or Twitter feed, and we hope to see you soon with more news from the natural world.